This unit of study is on the components and functions of mobile and fixed fluoroscopy. The objectives are to learn the terminology related to these units, to describe how the image intensification process works, to identify all the components and their functions in the process of acquiring images all the way to displaying of the images. So you're familiar with both types. There's fixed and there's mobile. Fixed are what we see in just regular general radiography departments, diagnostic imaging departments, and mobile are the C-arms that we use in surgical suites and other places. So there's similarities between the two. They both have a C-arm configuration with the image receptor and then the tube opposite that's connected with a carriage or arm. The tubes themselves are similar to X-ray tubes, but the main difference is that the MA settings are a lot lower. They're usually 0.5 to 5 MA, and you have to remember that we're using much longer times in fluoroscopy as we're exposing through a whole dynamic imaging series. The image intensifier itself is the image receptor, and it could be a flat panel detector in digital imaging, which we'll talk about in a later study. So there's a recording system typically that helps you to review a dynamic study. And then there's viewing systems that are attached. In the older days, they were cathode ray tubes, which are called CRTs, or flat panel monitors. And all of them now have a foot pedal exposure. So the image intensifier typically is above the patient in fixed fluoroscopy units, and it's contained in a carriage. So the image intensifier is a little bit more bulky and heavy to move, so it has a power assist function that helps to move the carriage. And there are shutter controls for collimation, brightness control that helps to regulate the tube MA. There's controls for turning on the video recording or for taking an image of a very small spot, are called spot imaging. So radiologic technologists are not medical doctors, obviously, so we actually should not ever be operating a fluoroscopic unit. It's really not allowed because we can't make a diagnosis off of dynamic study, but you might be asked to use fluoro to find the terminal ileum on a small ball study and then to take a spot image. Digital fluoroscopy units can also have this TFT or CCD type of image receptor, but again, we'll talk about that later. And the one thing you need to know, that the other difference is that when the tube is under the table at a fixed location, it can't be any closer than 15 inches to the patient. So the tube in fluoroscopy has a vacuum tube, just like in diagnostic static imaging. It contains an anode and a cathode and a filament. It has a protective coating or shield to absorb scatter and to limit the leakage radiation coming out of it. It has a cooling system of the dielectric oil, and there's fans to help cool it also. There's a port or a small window that the x-rays exit so that they're not attenuated. And there's high voltage cables at each end for producing the potential difference in the tube. So typically on regular diagnostic units that we use MAs in the 50 to 1,000 or 1,200 MA range. Early in fluoroscopy use, you couldn't record any dynamic imaging, but now with cine recording, well, actually we don't use that so much, but now with video recording, you can look at those images again. So if you remember those pictures from the first unit, the way the image was viewed was directly But now the image receptor is attached to a monitor. And these early monitors, again, were called this cathode ray tube, and these were very heavy and bulky. But now we have these flat panel monitors, just like we have flat panel televisions. They're the same thing basically, and they allow viewing from different angles. So the image intensifier, as we know, was developed in 1948 to increase the brightness of the fluoroscopic dynamic image. So the need to increase that brightness, as a review, was so that radiologists could use their cone or photopic vision, which was better to be used because it has better visual acuity and contrast perception. Photopic vision is about 10 times better than scopic vision in these areas. And image intensifiers themselves, they increase the brightness of the image 5 to 5,000 times through the light amplification process. So the primary beam enters the concave input window. So this is actually coated with a fluorescent material, and this absorbs the X-ray photons, and then it emits light photons, similar to in analog imaging where we use screens that exposed the film with light. Remember the lab we did with a flash? Well, that's the same thing. So these light photons are captured then by a photocathode of the tube immediately, so they don't diverge out. So now the photocathode has absorbed these light photons and it emits electrons. And just like in X-ray production, the negative cathode and the positive anode use their potential difference to accelerate the electrons towards the anode or the positive end of the image intensifier. So if you look at the image intensification from this diagram, you can see that one 50 kiloelectron volt photon hits the concave screen that's coated with this fluorescent material, and it transfers, or this process that changes the light to electrons, and then it changes the electrons back to light. That's the image intensification process. So one of these photons, X-ray photons, is amplified to 2,000 light photons. So the material of the input screen is called cesium iodide, which should sound familiar. And the concave surface actually helps to focus those photons. The diameter can range from 5 to 23 inches. And there's a protective coating that's between this phosphor layer and the photocathode. So there's no chemical reaction between the two types of materials. The cathode material is called cesium. Well, it has cesium and antimony, and it's called a photoemissive compound, which means that it absorbs the light photons and emits electrons. That's the photoemission process. And you can compare it to the thermionic emission that occurs in X-ray production at the cathode, except here the emission is created from light and not heat, as in the diagnostic X-ray tube. The electrostatic lenses, they work in a similar way to the focusing cups. They are negatively charged and they repel the electrons from the photocathode into a focus path that is an accelerant. Since the input is larger than the output, the stream of electrons cross and then they're reversed. So then superior is inferior and left is right. The crossing point of these electrons is called the focal point. So the anode is found immediately before the output screen. It's a circular disc and it has a positive charge that helps to increase the potential difference between the negative cathode. It has a small hole that allows the electrons to pass through and then to hit the output screen. So this phosphor at the output screen is different than the input phosphor screen, and it's called zinc cadmium sulfide. This layer is very thin and small, and that helps to provide better resolution. A small layer is then applied to eliminate any type, it's a filter that prevents any type of isotropic light emission from hitting back on the screen and degrading the image. Fiber optics are used at the output screen to gather the light in more modern systems. So there's a YouTube here that you can watch on image intensification process. Collimators are another component in fluoroscopy, and they're used for the same reasons, to reduce scatter and improve visualization of detail through the improved contrast resolution. Typically, they're round collimators. They're automatic and they're restricted to the field of view, meaning they won't get any bigger than the field of view. And then you can manually collimate with rectangular ones. And you can see on the second picture that the round image became more of an octagon. Another component is filtration. So the use of filtration is the same. You have to have a minimum of 2.5 millimeter aluminum equivalent, and you have to remember that some of that filtration is added, and that comes from the tabletop because the tube is underneath the patient. So sometimes in conventional fluoroscopy, you might use a 0.2 millimeter thickness of copper to improve the image quality and filter out those soft photons and harden the beam. This actually reduces the patient dose by 50% just by adding this small 0.2 millimeters of copper. Angiography and other complex imaging sometimes require additional filtration to be added. You have to think about the table, the way it's constructed. It's usually it's always radiolucent and made of a carbon fiber material. It needs to be strong enough that it can support a patient's weight, and that's usually why there's weight limits on tables, because you don't want any bowing of the table itself that could damage some of the equipment underneath. So the pads that you might use on the table need to be radiolucent. Gel pads have become a lot more popular, so a thinner pad is better. And if you're thinking about the table itself, it should tilt a minimum of 15 degrees Trendelenburg, but 30 degrees is actually more desirable for myelogram studies. Grids are another component. They range from 6.6 to 1 ratio to a 10 to 1 ratio. You have to remember not to use the grid for a pediatric exam or for a small part or small patient. You can actually remove the grid, so make sure you do that. They're usually not necessary because you're using a smaller field of view. And also the other thing that can be used is air gap technique, where you actually substitute a grid by raising the carriage up, but there are consequences to that, which we'll learn about more when we're talking about the technical factors. So optical coupling can occur at the output screen, and those are using optics to take the light and move it into a charge coupled device or a fiber optic system. Then that light goes to the analog to digital converter. Some systems at this point split the image. One of the parts of the image, or part of the resolution of the image, goes to the video recording system and the other to the viewing system. And this is basically a very simple system. It's usually a video camera and a television monitor. In older fluoroscopy systems, you could take spot films, and basically what happened is the radiologist would shoot an image. It would drag in a cassette. Then the technologist had to pull that cassette back out and manually put in another one. Now there's photo spot cameras that record the static images without any kind of disruption to the imaging itself, up to 12 images per second. The viewing systems, so they're actually used to view the image. And again, it's kind of a simple television device in a kind of a video camera. Sometimes what happens is there's an optical lens that is coupled, and that's just what we were talking about in the last slide. Sometimes you can read them being called vidicoms or plumicoms. And this is a type of television tube that took the output screen image and converted it into light. And then it actually reconstructs it on the viewing screen. And there's really nothing very magical about this process. It's very simple. We talk about it in digital imaging all the time. There's different kinds of monitors. There's CRT, cathode ray, and LCD. And these are some examples of that with some more details to the layers. You really just need to know what the LED, LCD stands for and recognize that. So let's do a little review. At what stage of image-intensified fluoroscopy is the number of image-forming photons the lowest? It's the lowest when they enter the input phosphor. The image intensifier input screen receives the X-ray photons. What's emitted at the output phosphor? Visible light. So what is the input phosphor material? It's cesium iodide. And the output phosphor material is zinc cadmium sulfide. And the photoemissive component of the image intensified fluoroscopy, it takes the electrons, it makes electrons from the light. So it's the photoemissive property or component.